Hi, I'm Mark Day, and my experiment research topic is the effect of rain events on the non-contact recreational use field assessment score in Waller Creek. So first, the question I decided to ask was, does the proximity of time since the last rain event affect the score of the non-contact recreational use field assessment form, or the survey, recorded by students? Alright, so getting into some background here, I wanted to start out with this survey that I'm referring to, which is this non-contact recreational use field assessment form. So this field assessment form, it's used by the city of Austin to sort of assess different bodies of water. And obviously it's a qualitative sort of survey. You're looking at different individual categories, such as seen to the right is the clarity, litter, flow volume, odor, percent algae cover, and surface appearance. So basically what's going to be happening is students are going to be going through and they assess the body of water that they're next to, which is the area in Waller Creek in our situation, and they're going to give it a score out of 20. So each of these categories are going to be added up together and it should be a total of 120. Now, whenever I was looking at this survey, I was realizing that a lot of these factors like clarity and litter, flow volume, etc., they're definitely affected by rainfall. And so I thought it would be interesting to look at each of these individual categories and look how the total score was going to be affected by the entire amount of rainfall that's occurring and the proximity to rainfall. So I was looking more into that idea. Now, getting into the locations I chose. So the locations I had to sort of base on, I wanted one that was closer in proximity to a rain event and one that was farther away in proximity to a rain event. That way I could compare how the score was going to be affected by rainfall in the area. So in choosing the locations, I had to look at ones that were taken twice. So students had to go down and take a survey twice. That way we can get an accurate comparison. So the three locations that had that were the Alumni Center, which is seen in the picture 1, farthest to the left, the Hemphill Branch, which is going to be referred as TJ, which is the picture in the middle, and then Clark Field, which is CF, and that's the picture all the way to the right. So whenever I'm taking this comparison of the survey data taken, I'm going to be looking at these three locations and seeing how they're affected. And it's definitely the same survey taken. It's just like I said, you had to take one that was closer in proximity and you had to take one that was farther away. That way we can get that accurate comparison. Now, let's get into the hypotheses here. So the survey score, due to the rainfall, it could either go up, go down, stay the same, or have no correlation whatsoever. So getting into each of these, if the survey score was going to go up due to rainfall, it would have to be based on these individual categories. So if you're thinking about stuff like flow volume, of course, flow volume might end up going up if there's more rainfall in the area, or it could make it go down maybe because it's flowing more out quicker if it's flash flood situation. So that's going to make sure whether or not the score is going to go up. And then if it's going to go down, that might be based on another one, say like clarity. If a lot of rainfall comes through, the clarity of the creek is going to be a little bit more murky. So that might cause the score to end up going down. So that was those two hypotheses. Another one is it could just stay the same. Now, like Waller Creek, because it's often so extreme, it might quickly go back down, which would mean the score would end up staying the same. So that was sort of my thought process there. And then also there's the possibility of no correlation, which is the null hypothesis, which is definitely a possibility as it could be due to the qualitative data, which throws it off, and it might just not have a correlation whatsoever. So I thought that definitely had to be a possibility. And looking at this urban creek syndrome, so the urban creek syndrome, I'll get more into it later, but that is another thing where the symptoms of that could cause it to either go up, down, stay the same, and it's definitely going to be interesting to look how the results affect that. Alrighty, so looking into the significance of it, it's definitely going to be good to see how it's going to record this aesthetics degradation. So getting into that, it's sort of like looking at how the beauty and like the enjoyability, I guess, of the Waller Creek is going to be affected by rainfall. So if more rainfall is going to come through, is that going to make it uglier? It's not going to make it as enjoyable. There might be more trash. So this results could possibly tell us how this creek is going to be enjoyed for the future. And especially with climate change, which is going to be causing a lot more inconsistent weather patterns. So that means there's going to be more droughts, but there's also going to be more flash floods. So looking at how this rainfall is affecting the data, especially with thinking in terms of climate change and how that's going to affect it, this data is going to be really significant in knowing the future of Waller Creek and how the community is going to be able to enjoy it. All right, so looking at my results now, transitioning a bit here, you can see to the right, I divided all the categories based into each of the areas, and then within each area, I said the one that was closer to a rain event and one that was farther away from a rain event. So if you're looking here, you can see each of them, it's that total again out of 120, and it obviously is a little bit lower of the scores, which tells you some of the degradation already of Waller Creek, and they're each based on these individual categories. So you can see here a part of it as well is there's definitely inconsistent amount of survey data taken at each location, which is another way that there could have been mistakes. It could have pushed towards the null hypothesis, which is why I started to get a little worried and why in the end I ended up having to run a t-test as well, which we'll get into later. And so in order to get more of my results, I took each of these numbers and each of these categories and I averaged them together, which is how we got to this point in the first place. All right, so now let's look at those averages. So here it shows the averages put into a bar graph, as I was saying before, and I chose the bar graph as it's able to show an accurate comparison showing which one is going down. So as you can see, it shows clearly the blue one is far after rain, the orange is close after rain, and you can see that the survey score obviously went down whenever it's close after rain. You can see that from each of the locations pretty clearly. CF is a little bit more close together, which is why I decided that the uncertainty was a little too much, and that's why I had to run the t-test as well. But at this point, it can be pretty clear that we're in between the null hypothesis and we're in between that the rainfall causes the score to go down. All right, so getting into the results, looking at it is the t-test first. So obviously we know the process of the t-test. First, I had to find the standard deviation of each of these categories based on their proximity. And using those standard deviations, I ran the f-test. And I found that because the F calculated was less than the F table, it was a type 2, which was with similar variances. And then I decided to go with a one-tail because I expected one of the scores obviously to be higher than the other because I knew that was the whole point of the experiment, which is see which one was going to be higher, which one was lower. So whenever I put that all into the Excel table, which you can see this is directly copy and pasted from my Excel table, I found that the p-value was equal to 0.05. You can see it's a little bit above 0.05, but it's 0.0504. So it's obviously at least 95% or maybe just tiny bit below. So I took that to be that the null hypothesis was definitely void, and I decided to continue with my decided conclusion, which we will now get into. So I concluded that the score for the survey goes down whenever it was closer in proximity to the rain event. Obviously, whenever I did the bar graph, also with the p-test, or p-value at least, that we can clearly see that the other hypotheses were actually going to be nulled by those results. So you could see from the bar graph and the p-test that that's how it happened. All right. So another surprising result was I decided to look into each of these individual categories because obviously when you look at the results, the only thing that really matters is the total score. But I wanted to sort of get into why these results because I was a little bit taken aback. So whenever you're looking at each of the individual categories, a lot of the ones that you would expect to be higher due to rainfall were actually still pretty low. So whenever you're looking at stuff like flow volume, you would expect after rainfall that the flow volume would go up, but from the scores, you can clearly see that the flow volume had gone down in each of those situations. So it kind of is trying to get into, and I wanted to start to explain with other research data that I found why this occurred. Because the only ones that were really higher, you can see in a few of these spots, is the rain events on like the odor score in CF. You can see it AC with the effect on clarity and the effect of the percent algae cover score in CF as well. But other than that, all of the scores were lower whenever it was closer in proximity after rain, which I found kind of surprising in terms of how the scores are taken. So in describing this, I found urban creek syndrome could have had a lot of the explanation to do of why this happened. So I took some data from this other report I found, which was called the urban stream syndrome, or the urban creek syndrome, where they were talking about how a lot of times the symptoms, it can cause much more frequent larger flow events and faster and ascending and descending limbs of flow, which could explain why that flow score was taken off so weirdly, is because if there was a rain event, it could easily be way higher right immediately, and then it could go way down. So it's like it could explain a lot of the situations we were seeing in those surprising results due to the symptoms of urbanization. So these symptoms of urbanization often can cause the efficient transport of runoff from impervious cover, which we were talking about before, which is caused by development. So it's causing more rain to flow into the creek and then more rain to flow right out of it. And so it's not keeping that consistent flow happening. And so whenever you're looking, that also could bring in a lot more pollutants, which could explain the clarity issue. It could explain the odor, the litter. So all of this efficient transport of runoff over these impervious surfaces could be explained by this urban creek syndrome that we're looking at. So looking at the significance of the results, it obviously shows this crisis that Waller Creek is facing, especially when you're dealing with climate change. So if you're having a lot more of these rain events that are completely inconsistent, it's going to create a degradation of the beauty of the creek. And this creek is obviously enjoyed by many citizens of Austin. They're walking around, they're seeing it, they're spending time around it. It's supposed to raise their happiness. It's supposed to be a lot of beauty in the city. But if we're facing if we're facing a lot of these issues, then obviously it's going to be a big issue in the future whenever we're going to be dealing with even more of this stuff. The only thing that these results show is that these effects are going to be getting worse in the future. So if we're already seeing this degradation of beauty happening now, then the results of my experiment should be a red flag to these officials who are seeing that the beauty is already being affected by these rain events. And imagine in the future, it's going to be just even worse. So this should definitely raise a red flag for these Austin officials, and hopefully they can start to draft legislation based on these results and trying to reverse this degradation, because that could be the only way we could get past this point. All right, so getting into the methods and materials was pretty simple here. The only thing you really needed was the actual survey itself, and you needed a pencil, obviously, to fill it out. So first, we had to visit the 3 locations the first time. So you had to visit Alumni Center, Clark Field, the Hemp Hill branch, and first you went to the first round. So our first round, it was either going to be closer in proximity to a rain event or farther in proximity to a rain event, depending on the date that went down, because each day it was completely different depending on whenever the students were able to go down. So the actual rain event that we're basing this on was on October 10th. And so if you see each of the 2 times that they were visited, it can tell you which one was closer in proximity and which one was farther in proximity. And that's how the results were going to be based off of. So these varied pairs of students each went down to each location. Each location was visited twice. It was closer in proximity based on that rain date, and then all of the data was used to average to create the bar graph, which will reach a conclusion, and then obviously we would go through the analysis of it, which would be the t-test, and that would sort of conclude the data we would see. Next, I just have my references when I was talking about the urban creek syndrome, and that's what I based a lot of my results and my discussion off of. And thank you very much.